Hello, in this lecture we'll find out the length of line segment AE. In the drawing we have rectangle ABCD. Inside this rectangle we have two semicircles. The radius of the big semicircle is equal to 2 units in its length, and the radius of this small semicircle is equal to 1 unit in its length. In addition, we know that side AD of this rectangle is equal to 3 units in its length. Our mission is to find out the length of this line segment AE. So, the radius of this big semicircle is equal to 2 units in its length. This is the radius that is 2 units, and the radius of this small semicircle is equal to 1 unit in its length. We know that ABCD is a rectangle, and therefore all the angles inside this rectangle or inside any rectangle are right angles. So this is a right angle. This is also a right angle. This is a right angle. And this is also a right angle. The next step, we define the relevant points to this question with letters. We define the center of this big semicircle, this point is point P. We define the center of this small semicircle, this point is point Q. Likewise, we define the touching point of those two semicircles. This point is point S. We define the point of tendency of tangent AE with this big semicircle. This point is point L. And finally, we define the point of tendency of this tangent AE with this small semicircle. This point is point G. In the next step, we'll do a construction, that is to say, we'll extend line segment AE and side DC of this rectangle ABCD by a straight line until they touch each other. And we will define the touching point, this point is point F. DC is one side of this rectangle ABCD, therefore it is absolutely a straight line. Then in the construction we extended the straight line DC by a straight line, and therefore the result must be a short straight line. So DF must be a straight line. If we focus on the upper side of the straight line DF at point C, here the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles in one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of DF at point C? We have this angle that is a right angle plus this missing angle. In total they must be equal to 180 degrees according to rule 3. And therefore this missing angle must be equal to 90 degrees in its size. So in the right triangle, in the right small triangle ECF, on this right small triangle ECF, we'll define this angle EFC as alpha. So in the right small triangle ECF, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right triangle ADF, in the big right triangle ADF, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. PL is the radius of this big semicircle, and it is equal to 2 units in its length. So we have the radius PL that is drawn to point L, that is the point of tendency or tangent AF with this big semicircle. So now we can implement all one in our drawing. So I click on all one. According to all one, the tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle, and we have also tangent AB. This tangent AB is tangent to this circle at this point M. In addition, we have the radius OM that equals to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule 1. So we can implement rule 1 in our drawing. Why? Because in our drawing we have the radius PL that is equals to 2. Again, the radius PL is drawn to point L, that is the point of tendency of tangent AE with this big semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius PL. If AE is perpendicular to LP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius QG that equals to 1. The radius QG is drawn to point G, that is the point of tendency of tangent AE with this small semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius QG. If AE is perpendicular to QG, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So in the right triangle LPF, again in this right triangle LPF, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha. According to the sum rule, that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the small right triangle, GQF, again, this is the small right triangle GQF. This angle equals to alpha. This angle equals to 90 degrees. Therefore, this previous angle must be equal to 90 degrees minus alpha. In the next step, we prove that the big right triangle LPF is similar to this small right triangle GQF. So I write it down. We prove that the big right triangle LPF is similar to this small right triangle GQF. So why those two right triangles are similar to each other? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. Actually, this is angle P and F. In the big right triangle LPF, and it is equal to this angle, this is actually angle QGF. In this one right triangle FQG. So repeat again. We have found out that angle PLF in the big right triangle LPF equals to angle QGF in the small right triangle FQG. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles. So we can write down that angle alpha equals to itself as a common angle that belongs to both triangles. So if we relate to this angle, angle alpha, as it is belongs to the big right triangle LPF, it will be defined as angle LFP. And angle alpha equals to itself. So if we relate to this angle alpha as it is belongs to the small right triangle is GQF, it will be defined as angle GFQ. So repeat again. We have found out that this equation means that angle alpha equals to itself. We just called to angle alpha two different names. Angle alpha equals to itself. It's a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So this is angle LPF. The big right triangle LPF, and it is equal to this angle, that is actually angle GQF, this one right triangle FGQ. So repeat again, we have found out that angle LPF in the big right triangle LPF equals to angle GQF. In the small right triangle FGQ, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we actually prove that all the triangles of the big right triangle LPF are correspondingly equal to all the triangles on this small right triangle GQF. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. We found out that the right big triangle LPF is similar. This is the sign of similar to the right small triangle GQF according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We derive that side LP, the big triangle LPF, over side GQ, the small right triangle FGQ, equals to side PF in the big triangle LPF over side QF in the small right triangle QFG. So I'll fill again. Actually, found out that side LP in the big triangle over side GQ in the small triangle equals to side PF in the big triangle over side QF in the small triangle. LP is the radius of the big semicircle, that is 2, over GQ. GQ is the radius of the small semicircle, that is 1, equals to PF. What is the value of PF? First of all, PS is the radius of this big semicircle, that is equals to 2. Here, PD is also the radius of the big semicircle, that is equal to 2. Here we have QS is the radius of the small semicircle, that is 1. QC is also the radius of this small semicircle, that is also 1. We define the length of side CF as x. Again, side CF or line segment CF equals to x according to our definition. So in total, PF equals to 2 plus 1, that is 4, plus x. Again, in total, PF equals to 4 plus x. Over QF. QF equals to 1 plus x. Again, QF equals to QC, that is 1, plus CF, that is x. So in total, QF equals to 1 plus x. So in conclusion, we found out that 2 equals to 4 plus x over 1 plus x. Here we multiply this equation by 1 plus x, and you get that 2 times 1 plus x equals to 4 plus x. So here we open the brackets on this side of the equation, and get that 2 times 1 is 2 plus 2x equals to 4 plus x. Here we subtract x from this equation, and finally we get that 2 plus 2x minus x is 1. So it is 2 plus x. This side of the equation we have 2 plus x equals to 4. Here we subtract 2 from this equation, and finally we get that x equals to 4 minus 2 is 2. So x equals to 2 units in its length. That is to say, the length of line segment CF that is equals to x is 2 units. So x equals to 2 units in its length. In the next step, we will prove that the biggest right triangle in this drawing, that is triangle ADF, that the biggest right triangle ADF is similar to the smallest right triangle in this drawing, that is triangle ECF. Okay, again, we prove that the biggest right triangle ADF is similar to the smallest right triangle ECF. So why the biggest right triangle ADF is similar to the smallest right triangle ECF? First of all, those two angles they are both equal to 90 degrees, therefore they are equal to each other. So actually this is angle ADF, the biggest right triangle ADF, and this is equals to this angle. This is actually angle ECF. And the smallest right angle, EFC. Repeat again. Actually found out that angle ADF in a big triangle equals to angle ECF in the small triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha that belongs to both triangles. It belongs to the biggest right triangle ADF, and it also belongs to the smallest right triangle ECF. So we can find out that angle alpha equals to itself as a common angle that belongs to both triangles. So if we relate to this angle alpha as it belongs to the biggest right triangle ADF, it will be defined as angle AFD. And angle alpha equals to itself. So if we relate to this angle alpha as it belongs to the smallest right triangle ECF, it will be defined as angle EFC. Okay, this equation means that angle alpha equals to itself. We just call to angle alpha two different names. Angle alpha equals to itself is a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees on alpha, therefore they are equal to each other. And those two angles, they are both equal to 90 degrees on alpha, therefore they are equal to each other. So actually, this is angle DAF. In the big right triangle ADF, and it is equal to this angle, this is actually angle CEF. In the small right triangle EFC. So repeat again, if we found out that angle DAF in the big triangle ADF equals to angle CEF in the small right triangle ECF, they are both equal to 90 degrees on alpha, therefore they are equal to each other. So we actually proved that all the triangles in the biggest right triangle ADF are correspondingly equal to all the triangles in the smallest right triangle ECF. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. So we actually found out that the biggest right triangle ADF is similar, this is the sign of similar, to the smallest right triangle ECF, according to angle similarity rule. And from the fact that the biggest right triangle is similar to the smallest right triangle, we derive that the following relationship exists between their sides. We will derive that side AD, the biggest right triangle AFD, over side EC in the smallest right triangle EFC, equals to side DF in the biggest right triangle AFD, over side CF in the smallest right triangle EFC. So repeat again. We will derive that side AD, the biggest triangle, over side EC in the smallest triangle equals to side DF in the biggest triangle over side CF in the smallest triangle. AD equals to 3 units in itself according to what is given as the question. So write it down. AD equals to 3 over EC. EC is the missing side, so we leave it as it is. And it is equals to DF. What is the length of DF? DF in total equals to 2 plus 2, that is 4, plus 1 plus 1, that is 6, plus 2, 6 plus 2 is 8. So total DF equals to 8 units in its length. Repeat again, DF equals to 2 plus 2, that is 4, plus 1 plus 1, that is 6, plus 2, that is 8. So in total DF equals to 8. Over CF. CF equals to 2 units in its length. So in conclusion, actually found out that 3 over EC equals to 8 over 2. 8 over 2 is 4. So 3 over EC equals to 4. Here we multiply this equation by CE. And we get that 3 equals to 4 EC. Here we divide this equation by 4, and finally we get that the missing side EC equals to 3/4. Again, the missing side EC equals to 3/4. This is the missing side EC. That is equals to 0.75. 3/4 is 0.75. So the missing side EC equals to 0.75. We know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AD equals to the opposite side BC. Again, in rectangle ABCD, side AD equals to the opposite side BC. But AD is 3, therefore BC must be also equal to 3. So BC equals to 3. What is the length of the missing side BE? BE must be equal to BC minus EC. Again, BC minus EC equals to B. So BE equals to BC. BC is 3 minus EC. EC is 0.75. So in total, BE equals to 3 minus 0.75, that is 2.25. So if we found out that BE equals to 2.25, so I write it down. If we found out that this 970 BE is equals to 2.25 units in its length. Again, we know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side DC equals to side AB. What is the length of side DC? DC in total equals to 2 plus 2, that is 4, plus 1 plus 4, plus 1 plus 1, that is in total 6. Again, DC equals to 6 units in its length in total. So side DC is equals to the opposite side AB in rectangle ABCD. But DC is 6, therefore AB must be also equal to 6. In the next step, I'll copy the right triangle ABE in a new page and we'll implement the Pythagoras theorem on this right triangle, triangle ABE. Side AB equals to 6 units in its length. And side BE equals to 2.25 units in its length. So actually, this is the right triangle ABE, the deformity from the original domain, again side AB equals to 6, side B equals to 2.25. AE is the missing hypotenuse, the missing side. Here by PT is the version for Pythagoras theorem. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Again, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle ABE is AE, therefore the square of the hypotenuse is AE squared, and AE squared must be equal to AB squared plus BE squared. So I'll write it down. Right triangle ABE, according to the Pythagoras theorem, AE squared equals to AB squared plus BE squared. AE is the missing side, so we'll leave it as it is. So AE squared equals to AB squared. AB is 2.25, therefore AB squared is 2.25. That's actually 6.025 plus BA squared. BA is 6, therefore BA squared is 6 squared, that is 36. So in total, AE squared equals to 36 plus 6.025. 36 plus 6.025 is 41.025. So if you found out that AE squared equals to 41.025, so here we take out of this equation and finally get that the missing 970 AE is equals to the square root of 41.025 is equals to actually to 6.408 units. And that is the answer to the question. I repeat again, we found out that the length of the missing side AE is equals to 6.408 units. So in the next step, I'm summarizing the lecture. In this lecture, we found out the length of this 97 AE. So in the domain, we have rectangle ABCD. Inside this rectangle ABCD, we have two semicircles. The radius of the big semicircle, this big semicircle, is 2. The radius of this small semicircle is 1. In addition, we know that side AD of this rectangle ABCD equals to 4 units in the center. Again, our mission is to find out the length of this 97 AE. So first of all, we know that all the angles inside any rectangle are right angles. So those 4 angles, they are all right angles. In the next step, we defined the relevant points to this question with letters. We define the center of this semicircle, this point is point P. We define the center of this small semicircle, this point is point Q. We define the touching point between those two semicircles, this point is point S. We define the point of tendency of tangent AE with this big semicircle, this point is point L. We define the point of tendency of tangent AE with this small semicircle, this point is point G. In the next step, we extended line segment AE and side DC of this rectangle ABCD by straight line until they touch each other. We define this touching point, their touching point, this point is point F. DC is one side of this rectangle ABCD, therefore it is absolutely straight line. We extended straight line DC by straight line and the result is DF. When you extend a straight line by a straight line, the result must be a straight line, therefore DF must be a straight line. So if you focus on the upper side of the straight line DF at point C, here the sum of the angles must be equal to 180 degrees according to rule 3 that says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of DF at point C? We have this angle that is 90 degrees plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. We define this angle again ECF as alpha. So in the small right angle ECF, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equals to 180 degrees, that is the sum of the angles in any triangle. Likewise, in the big right triangle ADF, this angle equals to alpha, this angle equals to 90 degrees, therefore this third angle must be equal to 90 degrees minus alpha according to the sum rule that the sum of the angles in any triangle is equal to 180 degrees. PL is the radius of this big semicircle. The radius PL is drawn to point L. Therefore, we can implement here rule 1. The radius PL of this big semicircle is drawn to point L, that is the point of tendency of tangent AE with this big semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius LP. If AE is perpendicular to LP, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius QG of this small semicircle. The radius QG is equals to 1. The radius QG is drawn to point G, that is the point of tendency of tangent AE with this small semicircle. And whenever your radius is drawn to the point of tendency, then tangent AE will be perpendicular to the radius GQ. If AE is perpendicular to GQ, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to the sum rule, rule 1. So in this small right triangle GQF, this angle equals to alpha, this angle equals to 90 degrees, therefore this third angle must be equal to 90 degrees minus alpha. Likewise, in the big right triangle LPF, this angle equals to alpha, this angle equals to 90 degrees, therefore this missing angle must be equal to 90 degrees minus alpha. In the next step, we proved that the big right triangle LPF is similar to this small right triangle GQF. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles, so we can write down that angle alpha equals to itself is a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if you prove that all the figures of the big right triangle LPF are correspondingly equal to all the figures of this small right triangle GQF. Therefore, those two right triangles are similar to each other according to angle similarity rule. And from the fact that they are similar to each other, we will derive that the following relationship exists between their sides. We derive the side LP in the big triangle over side GQ in the small triangle equals to side PF in the big triangle over side QF in the small triangle. Repeat again. We derive that side LP in the big triangle over side GQ in the small triangle equals to side PF in the big triangle over side QF in the small triangle. LP is the radius of this big semicircle, that equals to 2 over GQ. GQ is the radius of this small semicircle, that is equals to 1, and it is equals to PF. PF in total We defined the length of side CF as x. PS is the radius of this big semicircle, that is 2. SQ is the radius of this small semicircle, that is 1. QC is also the radius of this small semicircle, that is 1. So in total, PF equals to 2 plus 1 plus 1, that is 4, plus x. Again, PF equals to 4, and QF equals to 1 plus x. Again, QS equals to QC, that is 1, plus CF, that is x. So in total, QF equals to 1 plus x. So in total, we found out that 2 over 1 equals to 4 plus x over 1 plus x. Here we multiply this equation by 1 plus x. And so we found out that 2 times 1 plus x equals to 4 plus x. We open the brackets here and we found out that 2 times 1 is 2 plus 2x equals to 4 plus x. Here we subtracted x from this equation and finally found out that here we have 2x plus x is x, so in total in this side of the equation we have 2 plus x equals to 4. X plus x is 0. So 2 plus x equals to 4. We subtracted 2 from this equation and finally found out that x equals to 4 plus 2, that is 2. So the missing side here, CF is equals to x is equals to 2 units. In the next step, we proved that this biggest right triangle ADF is similar to this smallest right triangle ECF. So why the biggest right triangle ADF is similar to the smallest right triangle ECF? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha that is a common angle that belongs to both triangles, so we can write down that angle alpha equals to itself. It's a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we shall prove that all the figures in the biggest right triangle ADF are correspondingly equal to all the figures in this smallest right triangle ECF. Therefore, those two right triangles are similar to each other, according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AD in the biggest right triangle, or side AC in the smallest right triangle, equals to side DF in the biggest right triangle, or side CF in the smallest right triangle. I'm repeating again. We will derive that side AD in the biggest right triangle or side AC in the smallest right triangle equals to side DF in the biggest right triangle or side CF in the smallest right triangle. AD equals to 3 units in its length according to what is given as a question over EC. EC is the missing side, so we leave it as it is, and it is equals to DF. What is the length of DF in total? DF in total equals to DP, that is 2, plus PS, that is 2. 2 plus 2 is 4, plus SQ, that is 1, plus QC, that is 1. So 4 plus 1 is 6, plus CF, that is 2. 6 plus 2 is 8. So in total, DF equals to 8, plus CF. CF is 2. So in conclusion, we found out that 3 over EC equals to 8 over 2. Here we divided 8 over 2 is 4, so in total 3 over EC equals to 4. Here we multiply this equation by EC and finally found out that 3 equals to 4 times EC. Here we divided this equation by 4 and finally found out that the missing side EC equals to 3/4, so 0.75. So this is the missing side EC. This is equals to either 3/4, so 0.75. So what is the length of BE? BE equals to BC minus CC. Again, BC minus CC equals to BE. BC equals to 3 units in its length according to the rule that the opposite sides of a rectangle are equal to each other. So rectangle ABCD, side AD equals to side BC, but AD is 3, therefore BC must be also equal to 3. So BC is 3, EC is 0.75, and therefore the missing side BE equals to BC minus CC. Again, BE equals to BC minus CC. BC is 3, EC is 0.75, so in total BE equals to 3 minus 0.75, that is 2.25. Yeah. the missing side BE is equals to 2.25 units in its length. According to the sum rule, that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC. But what is the length of DC? DC in total equals to 2 plus 2 plus 1 plus 1. Again, 2 plus 2 is 4, plus 1 plus 1, plus 1 plus 1, 4 plus 2 is 6. So DC in total equals to 6, therefore AB must be also equal to 6. In the next step, I copied the right triangle ABE in the equation and implemented the Pythagoras theorem for this right triangle ABE. So this is the right triangle ABE that I copied from the original drawing. AB equals to 6, B equals to 2.25, and here by PT is a relation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle ABE is AE, so the square of the hypotenuse is AE square, and AE square must be equal to AB square plus BE square. AE is the missing side, so we limit as it is, so AE square equals to AB square. AB is 6, therefore AB square is 36, plus BE square. BE is 2.25, therefore BE square is 2.25 squared, that is 6.025. So in total, AE square equals to 6.025 plus 36, 6.025 plus 36 equals to 41.025. So in conclusion, we found out that AE square equals to 41.025. Here we took out of this equation and finally found out that the missing side AE equals to the square root of 41.025, that is equals to 6.408 units. Okay, again, the answer to the question is that the length of the missing side AE is 6.408 units. Okay, thank you very much.